Okay, Assalamualaikum. I would like to start this presentation with introduction. So, the refrigeration and air conditioning system are widely used in residential, commercial, and industrial application. They are important for food preservation, air conditioning, and industrial cooling. Most of these systems operate using the vapor compression refrigeration cycle, also known as VCRC, because it's simple, reliable, and cost effective. However, there's some problem occur in our project. So, the conventional vapor compression refrigeration system have a very low efficiency in our case. The existing system has a coefficient of performance, or the easier or the short term is COP, is only 2.5. This low COP is mainly caused by high compressor work and large pressure differences between the evaporator and condenser. As a result, the system consumes more electrical energy and has a higher operating cost. So the aim of this project or our project is to improve the performance of the refrigeration system. Our main objective is to increase the COP from 2.5 to at least 4.0. This is achieved by reducing compressor work using multi-stage compression. So we continue with our next chapter, the literature review, the basic VCRC. Based on previous studies, the vapor compression refrigeration cycle or VCRC is the most commonly used in refrigeration system. It usually uses a refrigerant R134A and operates through four main components: the compressor, the condenser, expansion valve, and evaporator. Although this system is widely used, research shows that its efficiency decreases when operating under large pressure and a large temperature difference. Now I will explain a little bit about refrigerant R134A. R134A is commonly used in domestic refrigerators and air conditioning system. It is non-flammable and operate at moderate pressure, making it suitable for practical application. However, studies show that improving the system design is more effective than changing the refrigerant when aiming to increase the system efficiency. So we did some research to improve the performance. Some methods we researched. Many researchers have proposed different method to improve refrigeration system performance. Yeah, this method include subcooling, intercooling, flash chamber, and multi-stage compression. Among this method, multi-stage compression is considered one of the most effective approaches to reduce the compressor work and improve the COP for our opinion. In a multi-stage compression refrigeration system, the compression process is divided into two or more stages. Intercooling is applied between the stage to reduce refrigerant temperature before the next compression. This method reduces the compressor work, lower the discharge temperature, and significantly improve the coefficient of performance or COP, like our goal of our project. Now we explain a little bit of the role of flash chamber and intercooling. So flash chamber separate vapor to second stage compressor. So liquid will go to evaporator. So the advantage is remove flash gas before evaporator and increase the net refrigeration effect. Studies report during we do our studies report efficiency improvement is increased by 30% or 60%, etc. So in summary, literature shows that conventional VCRC system have efficiency limitation. Multi-stage compression system can effectively overcome this limitation by reducing energy losses and improving system performance. Therefore, based on literature review, multi-stage compression was selected as the main method to improve the COP in this project.
My name is Manur Alisa Adriana binti Wan Muhammad Azwan. CD240137. I will present about design. 1. To improve the performance and energy efficiency of a vapor compression refrigeration system with an existing COP of 2.5. Second, to reduce compressor work and high discharge temperature that contribute to excessive energy consumption. 3. To implement a multi-stage compression system with intercooling to enhance thermodynamic efficiency. 4. To increase the coefficient of performance COP to 0.0 or higher. 5. To reduce operating costs and improve overall system reliability. In Figure 1, the basic vapor compression refrigeration cycle consists of 4 components such as compressor, condenser, expansion valve, and evaporator. It operates in the following steps. Evaporator. The low-pressure liquid refrigerant absorbs heat from the refrigerated space and evaporates into vapor. Compressor. The vapor is compressed to a high pressure and temperature, increasing its enthalpy. Condenser. The high-pressure vapor releases heat to the surrounding and condenses into a liquid. Expansion valve. The high-pressure liquid refrigerant is throttled to a low-pressure mixture of liquid and vapor before entering the evaporator again. Figure 2 for multi-stage compression refrigeration system. This method reduces the total compression work and enhances system efficiency. Cycle flow. Evaporator. Heat absorbed. Low-pressure liquid refrigerant evaporates by absorbing heat from the refrigerated space, producing low-pressure vapor. Low-pressure compressor. The vapor is partially compressed to an intermediate pressure. Intercooler. The partially compressed vapor is cooled before entering the second compressor. This reduces the required work for further compression. A flash intercooler may also be used to separate and utilize flash gas. High pressure compressor. The vapor is compressed again to the condenser pressure. Condenser. The high pressure vapor releases its heat to the surrounding and condenses into a high pressure liquid. Expansion valve 1. The liquid refrigerant may be partially expanded through a valve into a flash chamber to separate vapor and liquid phases. Expansion valve 2. Only the subcooled liquid portion proceeds to the evaporator after final expansion, maximizing cooling effect. Cycle repeat. The low pressure refrigerant returns to the evaporator. So this is a schematic diagram and TS diagram for basic vapor compression refrigerant cycle. From 1 to 2. Irreversibility in the compressor. From 2 to 3. Pressure drop in the condenser. From 3 to 4. Irreversibility in the expansion. From 4 to 1. Pressure drop in the evaporator. Schematic diagram and TS diagram for multi-stage compression refrigeration system. From 1 to 2. Irreversibility in the first stage compressor. From 2 to 3. Pressure drop in the intercooler. From 3 to 4. Irreversibility in the second stage. From 4 to 5. Pressure drop in the condenser. From 5 to 6. Irreversibility in the expansion device. From 6 to 1. Pressure drop in the evaporator. For proposed justification. 1. The basic vapor compression refrigeration system is upgraded to a multi-stage compression system with intercooling. 2. The objective is to increase the coefficient of performance COP, reduce compressor work, and improve overall energy efficiency. 3. The proposed system targets a COP higher than 4.0 compared to the existing COP of 2.5. Lastly, performance evaluation is based on a refrigeration load of 50 kilowatt. Proposed modification. First, multi-stage compression. The compression process is divided into two stages. Low pressure compressor, high pressure compressor. This approach reduce total compressor work, especially at high pressure ratio compared to single stage compression. 2. Intercooling between compression stage. An intercooler is installed between the two compressors. It cools the refrigerant vapor after the first stage compression. Benefits: reduce refrigerant specific volume, lowers work input for the second stage compressor, improve isentropic efficiency. 3. Subcooling at the condenser outlet. Additional subcooling is applied before the throttling process. This increases the refrigeration effect without increasing compressor power, result in higher cooling capacity. Proposed modification. First, multi-stage compression. The compression process is divided into two stages. Low pressure compressor, high pressure compressor. This approach reduce total compressor work, especially at high pressure ratio compared to single stage compression. 2. Intercooling between compression stage. An intercooler is installed between the two compressors. It cools the refrigerant vapor after the first stage compression. Benefits: reduce refrigerant specific volume, lowers work input for the second stage compressor, improve isentropic efficiency. 3. Subcooling at the condenser outlet. Additional subcooling is applied before the throttling process. This increases the refrigeration effect without increasing compressor power, result in higher cooling capacity. Effect and challenge. First, for effect, multi-stage compression with intercooling increased the COP from 2.5 to 4.0. The system delivered higher cooling output per unit of work, reducing energy consumption. Dividing compression into stages lower total compressor work and improve efficiency. Subcooling and flash chamber further enhance the refrigeration effect without increasing power input. Challenge of multi-stage compression system. Increase system complexity, additional compressor, intercooler, piping and control system. Higher initial cost, more components, increased capital and installation costs. Advanced control requirement, precise monitoring of pressure, temperature and flow is required. Space and maintenance demand. Large system footprint and more frequent maintenance. Intercooler performance dependency. Efficiency strongly depends on effective heat exchange performance.
Assalamualaikum. My name is Muhammad Bari, metric number CD250104. I will be presenting to you about the calculation of the project. So first, we need to do the either vapor compression refrigeration cycle. So from this cycle, we can get stage 1, stage 2, stage 3, and stage 4 of the cycle. After we get all of that, we uh, need to calculate the energy balance of the cycle, which is Q in and work compressor, and then we can get COP of 2.5. So to improve it, we use multi-stage cycle, which have 9 stages. So after we get all the information of the stage, we can calculate the mass flow fraction, which is x is equal to 1. Indicates that there are no flash vapor occurs, which is all liquid goes to expansion. So we can calculate the energy balance. So for the work input, or we call it work compressor, we have on this multi-stage we have 2 work compressors, so we need to calculate both of them. Work compressor 1 and work compressor 2, and we total it up, get the work total. So after that, we calculate the QL, which is Q in, and we can get COP of 5.08, which is suitable for our question in this project.
In part of discussion, the single-stage compression system has low efficiency with a COP 2.5 because the compressor weight is high at 58.89 kJ per kilogram due to a large pressure difference. By using a multi-stage compression system with intercooling, the compression is divided in two stages, reducing compressor work to 29.86 kJ per kilogram and slightly increasing the refrigeration effect from 147.23 kJ per kilogram to 151.76 kJ per kilogram. Although the flash vapor is found, the system efficiency improved due to the better compression process. As the result, the COP reaches efficiency to 5.08, exceeding the project target of 4.0. This higher COP lower energy consumption, reducing operating costs, and extend the compressor's lifespan, making the system well suited for industrial application.
My name is Khairunisa binti Shaharuddin. My number matrix CD240077. I want to present about conclusion. First, the single-stage vapor compression refrigeration system show limited efficiency due to high compressor work and large pressure difference. The implementation of multi-stage compression with intercooling effectively improves system performance by reducing energy consumption and enhancing cooling efficiency. Next, the improved system achieve a higher coefficient of performance and meet the performance target set in this study. Overall, multi-stage compression is proven to be a practical and energy efficient solution for modern refrigeration applications. So that's all from us. Thank you.